All right, guys, so today what we're going to talk about is section 5.2, which is going to involve taking the ideas from section 5.1, that is, taking an object and slicing it into small pieces, and instead of working on areas, we're going to take three-dimensional objects and we're going to cut them into volumes instead. So the central formula we're going to be using here is the old cylinder formula from pre-calculus and high school geometry. So the first question is, what is a cylinder? Most people, when they think about cylinders, think of right circular cylinders. So a right circular cylinder looks like this. And it's got a height, and it's got a radius. And the formula for calculating the volume of this thing is going to be the volume is equal to pi r squared h. Now you may have that memorized, but the structure of this actually gives us an indication of the general formula for cylinders. Because really what we've done here is this part, this is the area of the base. If you look over here, you can see that the circles that form the bottom and the top have the standard area formula, which is just pi r squared. So the pi r squared in the formula here is just the area of the base of the cylinder. And as long as it maintains that cross-section as we go up and down, then we just multiply by the height to get the area. And that gives us a formula for the general volume of a cylinder. So volume of a general cylinder. So I can just imagine that I've got some complex shape. And as long as that shape has the same base and top, that is, the cross-sections are the same all the way through, then the area, or rather the volume of this thing, if this is the base B up on top here, and this measurement is h, then the volume of this figure is the same as the volume of a right circular cylinder. But instead of using pi r squared, we just have that the volume of this is equal to the base times the height, where B is equal to the base area. Okay, so that's what we're going to use when we start taking complex objects and cutting them up into pieces. So in the same way that rectangles were the piece that we chopped two-dimensional figures into in order to estimate the area, cylinders are going to be what we chop three-dimensional figures into in order to estimate the volume. Okay, so what's the basic approach going to be that we're going to take on all these sorts of questions? So there's a basic approach to volume. So step one is going to be that we're going to take a solid and we're going to decompose it into cylinders of some kind, which are also called cross-sections. So we decompose a solid, by which you mean a 3D object, into cross-sections, or cylinders. Then we're going to approximate the volume of a typical cylinder and then, just as in the area case, once we have a typical cylinder, we can just add them all up. And so adding them all up, we can either mean a sum if we're doing an approximation, or an integral if we're trying to work exactly. So this next picture is not of a specific function, but it's supposed to give you an idea of where the formula that we're going to introduce actually comes from. So I want you to imagine for a second that we have a figure that looks like this. It's like a loaf of bread, say. And let's suppose that it's arranged on the x-axis in this way so that this figure starts at x equals a, and the x-coordinate of where it finishes is x equals b. And what I want to do is I want to decompose this thing into slices. So what is a slice going to look like? Well, we're going to get these pieces that look like this. You can imagine that we take this bread slice out of here. And if I could take that slice and I could find its volume, then I could cut the whole loaf up into lots of those slices and add them up to get an approximation for the volume of the entire loaf of bread. So we're going to use the cylinder formula to do this. A typical slice is going to be a shape that looks like this. It's this bread slice. And its volume is going to be the area of the base of the slice times its height. Well, height is this little skinny direction right here in the x direction. So the height for this thing is change in x. You can imagine on the big figure what I'm meaning is that this gap is supposed to be delta x. And the base area of that cylinder, well, that's going to change depending on where the slice is, but it's going to be a function of where the slice is located. So the base area, b, is actually a function of x. That is, where the slice is located is going to change the volume. So you can imagine here that the volume of this particular slice is going to be big and fat compared to something down here at the end where you're going to get these little tiny slices by comparison. But the idea is that as long as I've got some sort of mathematical function that tells me how the base area changes as I move from here to here, then I can write down a formula for the volume of these slices as I move. Okay? So really this is b of x. And so the volume of the slice that I'm looking at, the slice volume, is equal to the base area as a function of x times delta x. Okay, so let's look at the same figure now, but let's try to construct what the formula might look like for the volume of the entire object. So I'm going to draw the same object again. So here's our bread loaf. And you can imagine now that instead of cutting it up with just one slice, I slice it in many places. So I'm going to take this loaf of bread, I'm going to cut it into slices, and I'm going to try to compute the volume of each slice. Well, I know what the formula for that is. This slice right here, which we could think of as being the ith slice, has volume b of xi delta x. So the slices are all of equal width, but their location changes depending on which particular slice I'm looking at. So that's where the xi comes from. So you can imagine this is x1, this is x2, this is x3. Those correspond to the position that the slices are located in. So the volume of a given slice is bxi delta x, and that means that the volume of the whole thing, the volume of the bread loaf, is going to be equal to, well, it's going to be about equal to the sum from 1 to n of b of xi delta x. And that means that if I want to take this one step further and make the slices smaller and smaller and smaller and finer, that I can convert this into an integral using a limit. So this is where our formula for the volume using this sort of cylinder method comes from. V is equal to the integral from a to b, because that's where the slices start and stop, of b of x dx, where b of x is the cross-sectional area. Okay, so before we get into the examples, which are going to make it much clearer how this procedure works, I want to give you a guideline for how to approach these things in practice, a guideline that I'm going to be using as I compute these examples. So, the most important thing, this is vitally important, draw a picture. In many of these problems, it's going to be almost impossible to figure out what's going on without a picture. If you just blindly plug functions into a formula, you're often not going to get the correct answer. In fact, just like in section 5.1, it's easier to just derive the formula from the situation you're looking at than to try to memorize a formula and stuff functions into it. So what we're after when we draw a picture is we're trying to figure out not a representative rectangle, but a representative cylinder or a representative slice. So, for example, if I have an object like this, say where I take a curve, so here's y is equal to root x. And let's suppose that I rotate that object around the x-axis. So I'm going to take this, I'm going to spin it this way. What I'm going to get is sort of this cylinder-looking thing. And the cross sections of this, once I've taken root x and I've spun it this way, the cross sections are going to look like disks. But they're three-dimensional disks. That is, this is a little cylinder. So in this particular case, if we were trying to write down a formula for what the volume of this object looked like, we'd have to write something like the integral from, well, I didn't give you an a or b here, so let's say a to b, and I know I'm supposed to write down the base area as a function of x dx. So how can I find the base area? Well, this is a circle, and the distance from the origin to the function is going to be the radius of the disk that I just drew. So I've got this disk, and I want to somehow capture its volume. Well, the radius from here to here, this radius is the same as the distance from the x-axis up to the function. So r is equal to root x minus 0, because that's the distance that we have to go from the top of the function down to the origin. That's the radius of this disk that I've spun out around the x-axis. Okay? So when we talk about b of x, if we're spinning circles, that means we have to find radii. So the volume of this thing is really equal to, well, if this is equal to root x, then the volume of this typical disk, this volume is going to be root x squared times pi, because pi r squared. So the radius here is the same as the distance of the disk that we've spun out around the x-axis. And so generically, what this formula is going to look like is something like this. The volume for this particular shape is going to look something like the integral from a to b of root x squared dx, where the particular volume that you get depends on where you started this shape and where you ended it. Okay, so when you're working on these problems, the picture should give you what the formula looks like, as long as you keep in mind that what you're doing is adding up the volumes of cylinders, in the same way that in 5.1 we were adding up the areas of rectangles. So in the next 2 videos, we're going to talk about some examples that will hopefully clarify how this process works. All right, talk to you later.